right. Good afternoon, everyone. Can you hear me? All right. So welcome on this kind of gloomy-ish Sunday afternoon. We are excited to have Dave Dolak here. He was supposed to give a lecture last year, but a family emergency came up and he was not able to come. So we're so excited to have him here today. And he's going to be talking about rocks on the beach and how to do geology this summer. So please help me in welcoming Dave.
Also, metamorphic rocks could be formed by, if they're near where there's hot magma. So limestone is a common sedimentary rock, but when it gets heated, it turns into marble. That's how you get marble. And then sedimentary rocks, think of either of these other two as they get eroded. I mean, erosion is a big process on the Earth. Freezing and thawing, the water wearing down, wind wears things down, it bumps rocks into others. So rocks break down into their components of crystals, sand, silt, clay, different sized particles, and then usually the water carries them somewhere, or maybe the wind does, and then they can get redeposited and then over time rehardened just by pressure or by being precipitated by minerals in the water. But the important thing about sedimentary rocks to think of is they generally have some kind of layering. Now, layering is not banding. See, banding is a squeezing of the rock and the crystals line up in bands, but layering implies time. One layer, next layer, sort of like my bedroom, right? Though last week's clothes are on the floor and this week's clothes are on top of him. So it implies time. And something called the rock cycle is something every geologist knows, because each of these three major rock types is part of a continuum. So where you start, I suppose in theory the Earth started when it cooled, everything would have been an igneous rock. But now it's, all where it's at. So if you have an igneous rock and it gets squeezed by temperature or pressure or heated by temperature, you can have a metamorphic rock. If it gets pushed deep enough in the Earth and remelts, you'll wind up an igneous rock later. Both metamorphic and igneous can be eroded, and that's how you wind up with actually sedimentary rocks. The particles of those rocks form into various kinds of layers. Sedimentary rocks could get squeezed also, or reheated, and they could become metamorphic rocks, or they could get pushed far enough back down into the Earth to remelt completely. So it's part of the continuum. If you can, if you got to identify the rock, it already tells you where it's at on this and in its history. Okay, so that's a little bit about how these kind of rocks are formed. So rock basics next. Where formed? Where are they formed, and where do you find them? This is what makes our area sort of unique. Most places, the bedrock is by definition the first layer of solid rock in your area. It was formed there in your area. In our area, our bedrock is, if you've been past the Elmhurst Quarry, which is I think being closed now for part of the deep tunnel, or on the way to, going to Indiana, you go over the Thornton Quarry. Our layer of bedrock is something called the Niagaran limestone dolomite. It was formed here. Of course, here was a different place, but formed 400 million years ago under an ocean. Okay, but most of the rocks that I'm talking about here, that we can find here, were actually not formed here. Unlike you go to the Grand Canyon or somewhere, those rocks were formed in that spot. But we have another interesting part of the geologic story here, because something brought most of these rocks from far away to mix them all together on our beach on Lake Michigan. So again, we do have some local bedrock, but it's pretty far down. For example, right below us, it's probably 100 feet down, or on the beach on Lake Michigan. Again, these are just terms, autochthonous or olocthonous. It's comes from somewhere else. But erratic rocks, that's what rocks that came from somewhere else. Now, how could they come from somewhere else? Well, because of glaciers. So we're going to be talking about that. If you look at the upper Midwest, or the whole Midwest, where are the bedrock of things like igneous and metamorphic? Because if I describe them as being formed by molten magma or squeezed mountain ranges, just looking at us on the beach on Lake Michigan, you can imagine don't look like many volcanoes around here, don't look like many mountains. So how could we have those rocks? Well, if you go a few hundred miles to the north, starting in Wisconsin up into Canada, the rocks on the surface there, the natural bedrock, are one of those types. Because hundreds of millions of years ago, those things are happening there, and it's been everything eroded down to that. That is the bedrock there. Collectively, that's called the Canadian Shield. These are the oldest rocks in North America, and some of them are the oldest rocks in the world. I'm going to finish off my talk with something here, and I know there's some good specimens in the the museum about here. But these generally are old, billion to 2 to 3 billion year old rocks. They're generally either igneous or metamorphic rocks. That's what's at the surface of those areas. That rock, if you wanted to go and find it here, you'd have to go down about 5,000 feet. Okay, but everything above that, once we go north of us, has been eroded away. That's why you're down to the basement of North America, is one way we call it. I'm a bike rider, some of you know, and I've ridden my bicycle across the United States. I've ridden around Lake Michigan and Lake Superior. I did Lake Superior about a dozen years ago, primarily to see the bedrock at Lake Superior. So if you circle Lake Superior, these are the kind of rocks that you see at the surface. See that banding and twisting? That's a metamorphic rock. That's nice. And we have some deposits of magma that hardened into something called basalt. That was hundreds of millions of years ago, but that's actually the bedrock in those areas north of us. So take 3 weeks and ride your bicycle around Lake Superior. Sedimentary rocks are primarily, there's a few areas near Hudson Bay, but most of the rocks in the Midwest are sedimentary. They were formed by erosion into oceans in the last 400 or so million years. So they're not nearly as old as those other rocks. I mean, still old by our standards. This is our, of course, bedrock in our area. That's a view of the Thornton Quarry from the air, from the highway view. I used to lead field trips for the Field Museum down in there. That's 400 million year old rock formed when Chicago was under a marine ocean. You find fossils of, you'll see in a few slides, of what was living in those kind of rocks. So that's our native bedrock. Interesting little fun facts. It's called the Niagaran Dolomite. It's the exact same rock as exposed at Niagara Falls. Like you can trace, does this work? Oh, it's green. Oh, maybe it doesn't work on the screen. Okay, so that's our bedrock. Again, it's either at the surface in a few spots or it's 100 feet down, but it rises up along the shore of Lake Michigan here, Door County, the Straits of Mackinac, and again, it pops back out there, so at Niagara Falls. So it's called the Niagaran Dolomite. It's a picture that, if you remember, some of you may have heard that we actually turned off the American Falls in the late 60s to clean them up from the rock that was accumulating, which was natural, but people thought it was, I don't know, disruptive to the beauty of getting married in Niagara Falls. I don't know. How do we have all these kind of rocks on the beach? That's what's very interesting about our area, because the only rocks we should have here should be our native bedrock. But we have all these other things from different time periods and different conditions because of this. In the last 20,000 years, what we see out here, what we see across the, the street here in Oak Brook, is been formed by the glaciers that came down. And glaciers are basically just rivers of ice. Once ice accumulates either enough thickness and just squeezes out by its own pressure, sort of like the blob, it will move. It will pick up things and carry them along. And it's not just like a brittle ice cube in your refrigerator. Ice that's under hundreds of feet, thousands of feet, it actually is sort of semi-plastic, like silly putty. So it will pluck rocks out of bedrock. They'll be ground up inside the glacier, everything down to particles from pebbles to cobbles to sand to silt to clay. All that's in the glacier. If you've ever seen a glacier, traveled to Alaska or somewhere, this is a picture. I had some projects in my Argonne day in Alaska. These are, your typical mountain glaciers, and, that just looks like something that's moving. Most geologic things are pretty static unless it's a volcano erupting or an earthquake. But this is one of the things on a regular daily basis, you could see something moving. This is a glacier in the front on Mount Rainier National Park that I hiked up to. So it would, took its time coming from the top of the mountain. But I wanted to show that because really a glacier, it's not just a nice clean ice cube. It's filled with rocks. The things it's picked up along the way, it's ground down into various pieces. The ice sublimes off the top, just like if you leave your ice cubes in the freezer for months and they'll eventually are gone. They'll go from solid to gaseous state. So rocks wind up on the top. So these are rocks that have been picked up and traveled down from wherever they started on Mount Rainier. When the glacier finally reaches a point where it can no longer stay as ice, bottom of the mountain is not cold enough, Ice age pushed farther down south in North America, can't keep stays ice. Then, of course, what happens to the glacier? It melts. And all the rocks it is carrying, they don't go back up. They just drop. So it could bring rocks from other places. That's one of the unique sort of geologic processes that do that. And they could bring lots of rocks, small to big to giant. Who's ever been to the Big Rock at Morton Arboretum? That's as big as this room. So glaciers can move like a rock that big hundreds of miles. Of course, that rock is as big as this room, but that glacier was 3,000 feet thick. So really, imagine the Sears Tower, and that would be somewhere up there. So in perspective, but that's really what makes our area unique, because we have rocks from lots of different places that are deposited on the beach. So they're all mixed up, and that's why you have to separate them out to decipher the story. A little bit then what a glacier does. So when a glacier is moving, advancing, the climate is cold enough, the snow is accumulating into ice, and the ice is moving either down the mountain or 15,000 feet of it in Canada just squeezing out and moving down to us. It pushes things in front of it. It's filled with debris, as I mentioned, from everything from cobbles and boulders and sand to silt to clay. Eventually, when the glacier stops moving or the climate warms and it drops all of that material, collectively that material is called till. And it's just a mixture of everything from sand and silt and clay and boulders and pebbles and cobbles. The structure is called a moraine. So it could either be a nice even moraine as the glacier melts back, or it could, if the glacier stopped for a while and had more snow coming or ice coming, it'll build up, a little big hill called an end moraine. DuPage County sits on an end moraine called a Valpo moraine, but it's filled with this just loose material called till, and our bedrock is, below that. Oops. The thing we call the Ice Age peaked about 20,000 years ago. There's various geologic techniques. We know that it was, northern Canada, the ice was about 15,000 feet thick. So that's 3 miles. That's sort of like modern Antarctica. And it squeezed down, as you can see, down to the Ohio River Valley. There were several advances and retreats over as the climate warmed and cooled. But the final one is called the Wisconsin glaciation. That's the one that, when it retreated, it gave us the final landscapes we see here. And what's interesting is by sort of finding some of the rocks in the various layers of till, we can tell which way the glacier came from, because we can see which parts of the Midwest has that rock as its bedrock. So if it came from here, but then later on you have something here, they're going to be deposited differently. So it's the Wisconsin glacier, the final one. See, it went down far south is about Indianapolis, maybe Bloomington, Illinois. It sort of missed parts of Wisconsin. That's called the driftless area. Not exactly sure why it went around it. There's some very hard rock to the north there called the Baraboo Quartzite. That may have been cause for it. But that's sort of the general picture of the last advance of the ice sheet. It reached its peak about 15,000 years ago. And I went to graduate school at Indiana University in Bloomington, which is about here. So when you drive down, you go past Indy, and then about 10 miles, 15 miles later, you go to Martinsville, and you go off the big hill, and that's going off the end of the glacial moraine into southern Indiana, which didn't have glaciers. Or if you've been to southern Illinois, like the Shawnee Forest, it looks quite different because it wasn't glaciated in the last couple of glacial periods. Another bicycle thing, I took that picture in Lisle a number of years ago when that sidewalk, before they covered that up. But that's what our primary till looks like. Many of you have it in your backyard, It's just a mixture of sand and silt and clay and boulders and pebbles and other rocks that were brought down. Then the last 10,000, 15,000 years, of course, we had developed our organic soil on top of it. But this is the parent material sort of DuPage County. And then below that, at some level, would be our bedrock. Now, to separate out material in that till, it's sort of impossible. You can't sit there and pick this out. But nature gives us a good way to do it. And the classic sort of geologic experiment that you do this, or demo, is you do the sediment jar. You can put some till in the water in a jar, shake it up, and what happens? You stop shaking it, what's going to happen? The heavy stuff settles out first. That's going to be the sand, or the pebbles and then the sand. Finally, the silt might take a few hours, and it might take a week for that clay to finally settle out. The reason I'm going to mention this is everything in the till is mixed up. It's water that later separates it out. Water on the beach, so you can get the sand here and the silt here and the pebbles here. But all of it came down from parts north, in our case, in the glacier, and it's the front of that beach line of when the Great Lakes are there that helps to wash and continually sort of separate these things out for us so we can find them. Because if you would, in theory, everything I find here you could find if you go dig in your till in the backyard. Now, they wouldn't be as rounded because, of course, they've been rounded on the beach for 5,000 years, bumping into each other, and sand is pretty erosive. But you could find them, but you would never do it. It'd be impossible, use your mind. What you might find, though, is a lot of the rocks that I found here in DuPage County, they'll have scratches on them like that. And that's not construction equipment. It's inside the glacier, the rocks bumping around and moving. And you can see this in modern places where there's glaciers. There's no other process in nature that does this. So you go to the bottom of the Grand Canyon, and the river eroding rocks doesn't do this. Only glaciers do. So that's one of our big hints that we had glaciers here. I didn't bring a good eroded rock with me, but you can find, I found some really interesting ones in the Palos. Okay, rock basics 3. So we've talked about the basic kind of rock groups, how they were formed. We're talking about where they were formed, or at least in the upper Midwest, where they're found naturally. And so, next part, when were these rocks formed? Well, the Earth is about 4.5 billion years old. The oldest rocks on Earth are close to 4 billion years, and some of those are in Canada, exposed to the surface. I found this a few years ago in the Palos Hills. Every farmer's field, every year there's new rocks coming up, you know, granites and stuff. I was out with a buddy, and we were hiking down a little stream bed, and it was filled with glacial erratics, you know, rocks that the glaciers brought down and were eroding out of the till. Boulders of, you know, granite and basalt and our local dolomite from Door County that came down. Nothing exciting, but we saw this rock. It was quite interesting. And it was striped, it was really heavy, and I have my magnet here. Well, it's magnetic, and that tipped us off. This is banded iron. This is 2.5 billion years old. So I had it cut in half, and part of it's at the Camp Sagawau Museum, and my buddy's got a piece, and I got a piece here. But that came from far northern Minnesota. That's where that's exposed at the surface in the bedrock. So some of those rocks from the Canadian Shield, these basalts, these gneisses, these metamorphic rocks, they could be a couple billion years old. Our local bedrock and the sedimentary rocks are 300 and 400 million years old in general. Okay, the things that we're going to find on Lake Michigan. Of course, dinosaurs are 200 to about 75 million years ago. We don't have anything like that here. The glaciers took away all the rocks that are younger in time than 300 million years in our area. So that's another sort of important geology we'll show next is we have layers of rock are called strata, and just like my bedroom floor, the older things are on the bottom. Well, the glaciers that came through the Midwest took away enough rock that basically the first surface rock at our area is 400 million years old. And then since the glaciers were more erosive the further north we went, that's why in Canada, even older rocks are at the surface. They've even had more layers that probably were there at some point, eroded away. And you know, the general term for that is called superposition, which is oldest on the bottom, youngest on the top. And all of this is the signature work in geology. Present is the clue to the past. So we look at present processes, and we assume that if they were operating in the past, they would give us the same results. So I find a scratch rock coming out of a glacier, modern glacier today, and I find a scratch rock in my backyard in Downers Grove. Must have been a glacier here, you know, unless it was some process that doesn't happen anymore, or space aliens, you know, but that's not a very scientific way of looking at it. Question?
The rock that you have there, it shows when you cut it, it has all sorts of different levels. But how did you know that it had that inside? The outside just looks like an ordinary rock.
Well, it's got a lot of nice color here, and it was very heavy. So we noticed we had to have a lot of primary ore in it of some kind. The dark layers are the ones that are magnetic, and I don't know if I have a magnet with me. If somebody does, when you come up later, you can look there.
So the key was the weight.
Yeah, and then we had a magnet with us. And we go, that's magnetic. It's not just a piece of granite. And, of course, the striping. But, all right. So how do we identify rocks in the field, even figure out which of these categories it is? There's fancy lab techniques that one can use, but there are simple just field techniques that a geologist would use. You could look at them. What is the size of the grains? Big or small? Do they cool quickly or slowly? What's the color? What's the texture like? Some rocks are denser, heavier than others. You know, that banded iron, I knew it had to have something like an ore in it, iron or copper, because it was much more dense than just a chunk of granite would be. This is an interesting concept of hardness. Hardness is the ability to scratch or be scratched. And there's a scale from sort of 1, the softest thing, which is the mineral talc, to the hardest, which is diamond, on 10, and it's a logarithmic scale, so you know, it goes like this. But diamond is the hardest substance in the universe. Nothing can scratch a diamond but another diamond. On the scale, glass is about 5. So glass is something that geologists use as sort of to separate things that are generally soft from things that are hard, is geology. And hard doesn't mean strong. I mean, you can shatter your diamond into a million pieces, okay? Steel is only moderate, it's had a hardness of about 5, but steel is very tough. But hardness is a scratchability, but it's very useful for us trying to figure out the minerals and then therefore some of the rocks. So geologists will always have a piece of glass with them to use to scratch. Most minerals in igneous and metamorphic rocks, things like quartzes and feldspars, they're hard enough to scratch glass. Things for limestone, which is a common sedimentary rock, calcite, won't scratch the glass. So we can use these to sort of tease out. Your fingernail has a hardness of about 2.5. So talc won't scratch your fingernail, but you can scratch talc or gypsum. So that's, by having that simple piece of glass, it's a first sort of cut in separating out things that are going to be likely igneous and metamorphic from things that are sedimentary. Except sandstone is a sedimentary rock, because sandstone is sand grains that are just re-cemented, and sand is quartz. So sandstone is the one sedimentary rock that will be hard. But you can tell it's sedimentary because it can have layers. You know, and you'll see the grains. Certain rocks will react with acid, so usually we have a little bottle of dilute acid. That's diagnostic for a limestone and dolomite for our local rocks. It tells you there's calcite in there. You know, when you look at the crystals, do they look like they're just globbed together? Do they look like they're interlaced, so they cooled and fingered together? All of these help you determine which of those 3 major sort of rock types that you have. So these are simple field techniques you can use. And again, this is what you see. Igneous are generally dark in color, generally a little denser. They're generally hard. They're not layered because, of course, they cooled as magma. The crystals are going to be interlocked. They may be small because they cool quickly. They may be big to see with the naked eye, the various minerals, because they cooled slowly. Metamorphic, since they're the same basic minerals, they're generally dark and dense. They're hard, but they might have bands in them because they've been re-squeezed. See, they had a secondary thing happen to them. So the name of some of those rocks are gneiss and schist and quartzite, but granite, basalt, primary quartz, those things. Sedimentary rocks are generally lighter in color. Again, they're usually softer than glass except for sandstone, because sandstone is grains of sand. They're going to have some evidence of layering usually, and these are the ones we'll find fossils in. Because think of how they were formed. The sand buried organisms in the bottom of the ocean, or the lime precipitated to bury them, and nothing else happened. You know, molten lava pouring on a fossil, you know, on a trilobite is going to destroy it, right? You can probably imagine. Not many fossils in molten lava. Or if something was a rock that had fossils in it, it's got squeezed into the mountain range, fossils are not going to be very good there. So that's the big tip-off. And the big rocks that we'll find on the beach will be sandstones, limestone, dolomite, and a variety of quartz that redissolved and then rehardened is very popular find. It's called chert, but when it does it in multicolors and layering, you get agates. And these are really big, important things, especially people on Lake Superior look for agates. Now, a lot of fossils on Lake Superior beaches, because think about where Lake Superior is. Their stuff is coming straight from Canada, and it's all igneous and metamorphic. We get a lot of stuff on the beach from upper Michigan, Wisconsin, and that's still sedimentary rocks to mix in Door County, etc. So here's some of the things I have, and then when we're done, you can come on up here and look at some things. So here's some of the igneous rocks that I have. Basalt, generally dark color, dark green to black. The Hawaiian Islands are basalt because, of course, lava, it's cooled. And all the rocks I'm showing, why are they rounded? Because for the last 10,000 years, they've been on the shore of Lake Michigan, and sand is hardness of 7, eroded them. That's why they're all rounded and been eroded that way. The rhyolite is just another different chemical composition, but these both cooled on the surface basically quickly. Below the surface, igneous rocks, the big fancy one is granite. Okay, it's got 3 major crystals in it, mica, feldspar, and quartz, but they're going to be arranged pepper-like because it just cooled and the crystals cooled at random. So, and then we could term them, if they cool below the surface, we call them plutonic, and that's where you have things like granite, syenite, but granite's the main one you'll see. And then if they cool on the surface, they cool quickly. The crystals are generally small. Sorry, a lot of hay fever things this year for me. But rhyolite there. So some of the ages of those, when we go to those bedrocks, this is a geologic time chart. So if you look at the color coordinated there, you look at most of those rocks in that Canadian shield, they're down here in the range of 500 to 2.5 billion years old. Whereas the native bedrock in the lower part of the Great Lakes is in this range of 300 to 400 million years old. So these are the bedrocks. But we find them all mixed here at the beach. Again, I probably should have had the slide earlier because I've been to the Grand Canyon a number of times. But this is a good example of the idea of, remember, oldest to youngest. So I've hiked 3,000 feet down. I went back in time. These rocks are older than these rocks. Now, if you're in a mountain range and things are twisted around, then you've got to do some other things to figure things out. But generally, rocks are sort of arranged this way. And again, here's our age of the rocks in the Midwest using a geologic time chart. Maybe a little more detail than we need. Just a fun picture. All right, metamorphic rocks. Again, so these have been squeezed. And either there's new crystals involved or they're banded. That's banding. That's banding. The crystals are aligned because it's like if I'm Superman and I took this chunk of granite, squeeze it, I can get nice. So they've had some secondary processing to them. I'm looking across, before we get to the sedimentary, so this is a cross-section sort of across Lake Michigan from Green Bay. See, this is where our bedrock, down in our area is just below the surface. This would be Door County, where it's at the surface. And of course, it comes back to the surface on the other side of Michigan by the time you get to Niagara Falls. So that shows that the strata in the Midwest is a little warped. And you have to get down to those really old rocks, igneous and metamorphic. They're pretty far down in our area, but they're at the surface in Canada because the glaciers took away all of those other layers up there. And here in our area, they took away everything above that, which would be dinosaurs. In geologic time, anything up above that time period would be dinosaurs, but we don't have any in this part of the country. All right, sedimentary rocks, generally light in color, a little bit lighter in density, and generally not hard on the scratch level unless they're sandstones. But you can have sandstones, which of course is sand that was deposited not by Lake Michigan sand, but by some ancient beach sand 400 million years ago. And I think I have, I'll have something else on here too. So they'll generally be layered. Here's a chunk of sandstone from the beach. The lights, but you can see it's layered. That's limestone, and it's precipitated calcite. That's our basic rock in our area, our bedrock. And since sedimentary rocks are rocks put back together, you can have the sand cementing other little pebbles and stones, and that's a rock called conglomerate. It looks like concrete, but it's sort of a natural version of it. But those are things you find on the beach there. And you can find these agate things, which are a kind of quartz, and that's what I wanted to show here. It's primary quartz, or it's redissolved and precipitated quartz. It's not the primary quartz, beautiful crystals like you can see in the museum here. You have some beautiful quartz crystals that would be formed in igneous rocks. But quartz dissolves over time, and it can be reprecipitated into this form that we know as flint or chert. And again, if it does it in a time sequence with slightly different impurities of other minerals, it'll layer them, and you get these things called agates, which are highly prized on the beach if you can find them, especially Lake Superior agates. Okay, so we talked about these. It's a mixture of rocks from different places, were formed under different conditions at different time periods, but they're all found in the same place on the beach. And the sedimentary rocks have fossils in them often. So that's going to tell us a story about primarily animals, because this was mostly ocean life that we have here, that lived when those rocks, wherever they're from, were formed. And there's a number of interesting fossils that's what I like to look for on the beach that I'm going to show you with. And we're going to finish off with, well, we have modern things on the beach. And there's a lot of debate about, do we have a new geologic time period called the human-made time, but you find a lot of other things on the beach, and sometimes you can confuse them with other things, and I'll show you some pictures. All right, but when we start talking about the first of all, time, but all the animals, so when this was all happening too, when these rocks were formed, North America, the Earth didn't look like it does now. Our bedrock, 400 million years ago, was formed, this would be northern Illinois. See it here, this would be sort of North America. There's Hudson Bay. There's not even the Great Lakes yet. We are near the equator. We are under a shallow ocean. So you expect to find things that were living in a modern ocean near the tropics, corals and things like that. So, and even before that, when North America was further this way, that's when there was a lot of volcanoes erupting. That's when these kind of rocks were formed. Of course, 300, 400 million years of moving 2 inches a year, now we're up here. So when these things were living, it's not just a different time period. We weren't even in the same place. Lots of different stories you can tell here. So our native bedrock in the Midwest contains fossils of these kind of things. We have trilobites, lots of different kind of corals. And then there's trilobites and horn corals. And the two main things you'll find at the dunes and on the beaches of Lake Michigan are various kinds of corals, and these are my favorite, crinoid stems. Crinoids are an animal. They're related to starfish. They lived on a stalk. The heads don't preserve very well. They get sort of eroded as the rocks come apart. But the segments that kept them up are very common. I have a whole necklace made out of them. Every time I go to the beach, I've got to find another crinoid stem. Okay, that's my thing at the Indiana Dunes. So they're called sea lilies, but they're actually not a plant. They're an animal, but that's what they looked like in life. Other parts of the country, there's some really good fossils preserved in Indiana of heads of the crinoids in different strata, but they would be destroyed in the wave action. But the stems are pretty tough when they fossilize. So I've got lots of crinoid stems. And then corals. Corals can be honeycomb-like. There's a modern sort of equivalent of a coral. So you can see sort of the layers almost look like, beehive kind of structure, things like that. And I have examples of all these up here. So there's a fossil coral, and that's what you would interpret it to look like with the various, as the coral grew and the corallites kept moving up and building up their coral reef. And of course, one of the famous stones on the beach is Petoskey stone. Who's ever heard of Petoskey stone? I'm sure they got beautiful Petoskey stone here at the museum. That is it's the state stone of Michigan, but it's actually a fossil coral. You probably can buy some. Do we have some of the, no, you don't have Petoskey stone? Are you out of it or you don't stock it? Well, you go online, get Petoskey stone. But it's a type of coral. Now, when you find it on the beach, course, it's not very distinct until you get it wet. Then you can usually see. And you can see, no. But when you get it like this at, the rock shop or something like this, it's been polished up. But that's comes from the Petoskey, Traverse City area of Michigan. That's where its rock is at the surface. When I find it down here on the beach, that means it traveled this way. Just like I know this came from northern Minnesota because that's where that kind of rock is at the surface. See, this is how we can all sort of tell the direction of the glaciers. So there's my crinoids. Again, this is the kind of fossil you'd find in other strata in other parts of the country where you'd have a whole crinoid preserved. But here, when that kind of rock got exposed at the beach and in the glacier grinding it down, basically the segments all come apart. You find the stems. Some people call them Indian beads, and maybe Native Americans used them also for decoration, but again, they have nothing to do with Native Americans. I've got some chunks of the limestone that the crinoid stems are in. So something like this in another 100 years or so, probably the stem will have eroded out because that will be softer than the stem. So, they were originally in rock, but as the rock breaks down on the beach, this piece of sandstone is sort of interesting. It tells a story. Okay, so there's the layers. So the sand was, deposited on that beach when North America was down at the equator. That's when it hardened into sandstone. But these neat holes vertically through it, those are worm trails. So, if you've been to the beach on the ocean now, you see worms. They pop up right at the shoreline. Well, there were fossil worms long ago, sort of lived the same way. So I can sort of, interpret what that is, telling me. It's rare to find anything else besides corals and crinoids. Brachiopods are a type of shell. I found one decent brachiopod. They're real common fossils in other layers, especially in the Thornton Quarry, but they seem to have been eroded away on the beach. And I think I found one part of a trilobite. Not real sure. That's it. I think it's part of the central axis there, but I'm not sure. This is another type of coral. So these are all from the 300 to 400 million year old range. Our local dolomite, again, local 100 feet down or at Door County. By the time it gets down here, it's also eroded. But there's also tar and oil in that. It's an oil deposit. And in southern Illinois, they actually mine. So some of it I found pieces of tar. Of course, when the glaciers were here, there were things living on the glaciers. And it's very, very rare, but you might find something, too, in the beach from this time. And I found one thing, and one tour I led at the dunes a year ago, somebody else found something else. I should have told her, that's nothing, and I should have grabbed it. But anyway, I found this when I was working 40 years ago at the Indiana Dunes. That's a tooth. I have it here. It's a milk tooth of a mammal. So milk tooth is a baby tooth, right? They don't have roots. Remember, you lose your teeth. It's some ice age mammal. It's hard to tell just by milk teeth what it is, but that is a tooth of a mammal that was living during the Ice Age. Of course, here in DuPage County, occasionally they do dig up things like mammoths and mastodons, like go to Phillipsburg Woods. But on the beach, it's very rare to find anything like that. So that's only that, and the one thing that person found, the only two that I'm aware of. Now, you might go, why do you have it? It's a national park. So I'll answer questions later. Because I have to do this at the dunes when we do our tours. Another interesting thing to find is, lightning hits the sand, right? And it'll melt the sand grains because what is glass? It's just melted sand. And if lightning hits the sand, the dendritic pattern of the electricity will melt the sand grains into something called fulgurites. I got one part of a fulgurite here that was part of a bigger one that friends that I found. Everybody took a piece, But it's interesting because you can see that it's heated, it's melted on the outside with the primary crystals on the inside. This was part of a bigger chunk, and bigger chunks have gone away. Maybe they have fulgurites for sale in the shop here, I don't know. And then the last little bit. So now we've taken, rocks that are billions of years old that could be mixed in on the beach that were formed under different conditions. that are exposed hundreds of miles from us that are brought down. We have 400 million year old rocks. And then we have things that you find that are 100 years old or less. A lot of junk on the beach, right? You know, there's a lot of debate in geology. Should we call, since 1950, should we call a new geologic era the Anthropocene? And right now they're, you know, no, is the word, you know, because that's when we really started to affect the Earth in a big way with things like that, when I, of course, my work at Argonne, and now with climate change. But you'll be hearing about these debates for a while. But you find things on the beach that are not billions and millions of years old, but hundreds, tens, things like coal. There shouldn't be any coal found on the beach here. There's no deposits nearby, but I worked in the steel mills. Coal falls off the barges going into the steel mills. It's going to get rounded in just like anything else. Slag from the steel mills. I found this this bone a number of years ago. I thought, oh, that's cool. It's a bone. It's fossilized. And I go, well, why was it cut like that? Because it's cut. It's a beef bone or something, but it's been sitting in the beach long enough to be eroded. You know, asphalt. You know, there have been towns built near the beaches that have fallen in. You can find. I go, that looks like a pretty cool piece of conglomerate. No, it's asphalt. I found this 40 years ago, and I thought, this is pretty cool. It looks like a fossil plant. But, you know, I know the geology of the area. There shouldn't be any plants in those rocks. And it does look a lot like concrete with rusted iron and the holes like where screws were. So that's like an old pier that had broken down, but it's been in the sand long enough to erode away. Bricks, clay pots, again, all of them are going to be eventually eroded by the action of the waves back and forth along the sand. So that's some kind of a clay pot. Maybe somebody had a house along the beach there. And of course, other people, I'm into crinoid stems, other people are into collecting beach glass. Right? There's a whole group of people that collect beach glass on the lake. So how long does it take to go from a sharp piece of glass that would cut you to, you know, not that long, a few years, because sand is pretty hard and it's harder than glass, and rolling around in that sand, it's going to frost up, and, you know, there's various colors, and, you know, people do artwork on that, but there are a lot of beachcombers who are looking for sand, for beach glass. And then even more recent, you can find little pieces of modern shells. These are not fossils, but things like the zebra and the quagga mussels, which are invasive species that have, you know, taken over the bottom of the Great Lakes in the last 20 years. They wash up on the shore in moss. So, to finish off, the rocks that you can see on Lake Michigan and the beaches in the Great Lakes are unique in a lot of ways, because you could find rocks from different time periods, different environments, and different places all at one place. That's sort of unique in geology. Usually you don't have that. You know, the Grand Canyon, you have a lot of time periods there vertically from the bottom to the top, but all those rocks formed there. But here, these are rocks that, except for our local limestone dolomite, were not formed here. They formed under different kind of conditions in different places. Of course, North America's in a different place. They're exposed naturally in different places now, but they were brought here because of the unique things that we've had, glacial action. So, you know, the time. So on the beach, you could find rocks from 500 million years old to 2 billion years old and 10 years old. Again, the sedimentary rocks with fossils are in that 300, 400 million year old range, and then whereas the igneous and metamorphic rocks are older, and again, very rare. Maybe you can find something like there. So, and then they tell you different environments. These rocks were formed by heat and or pressure of long ago North America tectonic activities that are really not happening in our area now, or they were formed when we were below an ocean, not a freshwater lake that's only 10,000 years old. And, you know, all of this is because these were transported to us by glaciers. And then again, come from different places. The igneous and metamorphic, they're exposed hundreds of miles to the north of us. They're essentially the basement of North America. We'd have to go down very deep here to find them. Sedimentary rocks are our bedrock, but they were formed when we were near the equator. in a shallow ocean. And so the only thing that you can actually say was formed here in conditions we sort of look at now, even though the ice is gone, would be the sand, silt, and clay that the glaciers brought down in, last 15,000 years ago. So, but they all can be found in one place, the beach on Lake Michigan. And they're all part of that original till, like that's in Lake County or DuPage County here, but it's that action of the water. That's why I mentioned that sediment jar thing earlier. Over thousands of years, washing back and forth, the sand, then the wind blows the sand a little further up, the pebbles stay at the water line, and you have to go further out, and that's where this clay settles out into the water. So, there's that picture online, I don't know, Happy Rock.